So hope my screen is visible.
Yes, sir.
So as you told, you want to know about the binary search tree, right?
Yes.
Correct? Binary tree. So as a concept, in first you have to create some tree data structure, right? And the tree like in this way. This is the node, and the one node can contain another node, can contain another. So generally in binary tree means generally the one node can have a maximum two child. So you can say this is the binary tree. Binary tree means this is the one node, and this have a again one child or two child maximum. Similarly, this is also a node, so this can be also one child node or another child node, or similarly one child node or another child node, right? So in this way, generally kind of in this is the binary tree. So generally in the our programming language, first node of any tree generally considered as a root node, okay, and all other node as a just a node you can say. And if any node does not have any left pointer and right pointer, or you can say by default null, right? Null. So such node like this node, there is no any left, there is no any child, right? Then you can say this is your leaf node. So these are the leaf node, leaf node, leaf node, leaf node. Is it clear? What is the root node and what is the leaf node? Any doubt till now?
No, sir.
So is it
No.
clear? Yes.
No
Hello.
doubt, sir.
So up now the point come. This is the basic tree, and here whatever the value you want to play, you can place one value, two value, three value, four value, five value, six value, one value, any value you can place. There is no any restriction. So if your tree is a simple binary tree, so here the content or data part you can place any data. There is no any kind of restriction. Okay, any value can place here, but your binary search tree is a special kind of tree. They have apply some restrictions. So this binary search tree say if you have any root node, okay, so whatever value you are storing, like let's store 7, so all the left child, this is the left child, always be less than your root. So here you can only place value like 3, 4, 1, 2, 5 till 6. And all the greater value you can always place that the right child. If you want to store value like 8, 9, 10, yeah, anything, so that will be placed right hand child. So this is the condition for any binary search tree. All the tree can have a two node, but all tree you cannot say is the binary search tree. Binary search tree is the only tree which can follow this rule. Rule number one: all the left child must be less than your from root value, and all the right child value must be greater than or equal to your root value. So here this is the complete left child. So all the value, whatever value you are storing here, must be less than the root value. And here this is the another subtree. In this tree, all the value must be greater than from your root node. Is it clear?
Yes, sir. And so if we have the same value,
Hmm. So generally, Generally, in the while storing same data multiple time, that not makes sense. But if you want really know, I want to store the same value maybe 7 2 times. Okay, so you can take your decision. I am going to store equal to value on the left side or right side. You decide. Let's say I decide I'm going to store right side. So you can make some condition. But generally, we avoid to storing. Why you are storing 7 2 times, right? What the need? Generally, so if sometimes someone asks, can I put duplicate value in a binary search tree? Logically, programming language is not enforcing any restriction, but you can surely store. But generally, in a binary search tree, is the kind of a sorted search tree. So here, all the element generally try to store one times. Okay, but you can, if you want, you can tweak the theory and say, generally, if you read the definition, say left should be less than and right should be greater than, right? But you can say I can want to store same value again. So you decide key equal to value of the root I am going to store in the left side or right side, and whole logic you can write in the same way, right? But generally, while writing code, we avoiding writing the why you are storing duplicate data, right?
Yes, sir.
So is it clear what is the binary search tree? So binary search tree can be implemented in a two mode. Okay, one, if you have a like array data structure, right? If you have any array data structure, and if your array data structure is sorted order, okay, sorted order, then you can apply the binary search algorithm on the array as well as, okay, or any tree which follow this condition left and right, you can apply binary search on the tree data structure as well as. So binary search tree is a one searching algorithm that can be implemented in both data structure, even as a array data structure or even as a tree data structure. Till now, any doubt?
No, sir.
So I'm not exact clear. You want to implement binary search tree in the tree data structures, or you want to implement binary search tree in your array data structure? Because this is the one searching algorithm. But whenever you are going to apply this algorithm, binary search tree, this is my prerequisite. If you are going to implement on the array data structure, your array must be sorted. If you are going to use any tree data structure, your tree must follow this rule: left always less than and right always greater than. So this is your theoretical part.
Yes, sir. We have sir did like binary search in arrays.
Okay. So let's understand the concept about key binary search tree, how apply in array data structure, right? So first condition for array data structure, your array must be sorted order. First condition. If your array data structure is not sorted order, you cannot apply binary search tree algorithm to finding any searching any element. So what the algorithm say? If let's keep first condition meet, your array is sorted. Let's keep here any data you can place here like a 5, 7, like a 13, like a 20, and like a 25, right? Let's assume this is the sorted array. Surely say sorted array. So here you can apply binary search tree algorithm to searching any element. Binary search tree is a search algorithm if you find some element exists in a particular array or not, or in a data structure. So what algorithm say here? Here say let's this is a complete your array length, just you divide into the two part. Okay, just you divide into the two part. Just divide array into the two part. So let us, I want to search like 13. Okay, if 13 exists or not in this, so binary search tree, if first your 0 position, this is your n position, last element. The first you, what you do is just divide your complete array in a two part, in a half part. And now in a half part you are getting some value. Let's here example our 1 2 3 4 5 6, your 6 length. Okay, so if you divide in the two part, so what the middle element, so you say what is the middle element here? If your this is the array, what is the middle element? Tell me
13 and
what.
20, sir.
Eh?
We have
Middle
two
element
middle
can be
values.
only one, right? So generally what say, you say index position 0 and index position last here, like 0 1 2 3 4 5. So you say 0 plus 5 divided by 2. So what will be answer? You are getting 2, right? So by default this is your middle number. So you have to check the array of middle data is matched with my search element or not. So in this case found. So similarly check your data found. So let's assume I want to search here 25, for example, right? 25. So surely mid element is the not found here. So what the surely you, let's, if your 25 is greater than to the mid element or less than. So you notice 25 is a greater than your mid element. If it is a greater than, surely this is the sorted array. So 25 is not available in the left side, right? You can just ignore this complete array and you can just again search only this element, right? So again you divide this element to the two part again. So now here your index is a 3 and here a 5. You say 3 plus 5 divided by 2. So what is the middle element? Middle element equal to, here your
4.
index is the 3, here is a 5. 3 plus 5 divided by 2, what you are getting?
4.
4. So now your mid element is the 4. You are getting a 4. So again you compare this. 4 is matched with this. Yes, then return. Else not match, then again you check. This value less than or greater than. If value finding element is the greater than, then you can search rest value, or else this again left shift. So the logic here is that what binary search take you, whatever you have a tree, any number of length. First you divide half part and check with the middle element, whatever the value you want to search, this value. If this value is the less than or greater than with this value, if this is the less than, that means surely your element always come on the left side, not on the right side. You just again you do half of here. Again check this element is find with this middle element or not. If find or not. If not find, then it must be or less than or greater than. If this is the greater than, then you have to again this subpart again divide half and again check this element match with this or not. If not, again figure out it is less than or greater than. If let's say less than, so again only this part. You again divide then half and figure out your data. So in short, they always divide your array in half part and checking your finding element in which direction, left side or right side. If right side, again divide half. Again check your element in the left side or right side. The same rule they apply here. If your search element is left side, then you only search in the left direction. Or right side, then right direction. So this is the simple binary search algorithm say. you have any array data structure, then what you can do, first you just find out the middle element and check this middle element is exact match with the searching item or not. If not, then this search item is less than or greater than. If less than, then you have to only again same rule do again half and again check. If you greater than, then just half other part and again divide and again check with your this element. If again is a matched or less than or greater than. If greater than, then you again search in only half part. So this search algorithm, if you talk about the complexity, if your element, let's give we have a 100 element, so you are just first time checking half 15, again half 25, again half 12. So you can compare or find your search element with a minimum number of comparison. If not, then finding this search element in the 100 element might be you want to find 99. So you have to compare 99 times for each element. So binary search algorithms given a facility don't compare your search element by one each element. Okay, instead you can just find with the middle element. If middle less than or greater than, then again half, then again half. So you are drastically reduce your number of comparison to finding search element. Is it any doubt till now?
No, sir, that's clear.
So this is the approach for your tree data structure. Similarly, approach apply for your sorry, whatever discuss the same algorithm for the tree data structure. Now this is the tree. You know, okay, this left always less than, and this is the greater than. Again, this is the left greater than. This is always greater than. This is the left, and this is the greater than. Okay. Now let's. This is the complete your tree available. And if someone want to search particular element, okay, it exists or not, the first they are going to the root here and check if root data found with the search element or not. If not, it is a less than or greater than. If it is a less than, so only left subtree you going to search. Now you discard the right one. Again here you check this element is matched with this element or not. Not, you can check it's a greater than or less than. If greater than, then only this subtree you are going to again search. You are just discarding this one. Again you come here, this is matched with this, yes or not. Not, let's not match. Then again check less than or greater than. If less than, go again here and you found the element is exist here. So the same approach is the same. Binary search tree algorithm is the same. Where you are implementing using the array data structure, then you have dividing half and half. Here binary search tree automatic divide into two part. You just move your left or right. If your value greater than here, then you move the right part. If value greater than, then move right part. So approach for binary search algorithm is a simple. You search your element in the half data. Again not found, again half your array. Again not found, again half your array. And you can find this search element. Why this algorithm works? Because binary search tree have a precondition. For array, your data must be sorted. For tree, your data must follow this condition, left less than and right greater than. Due to that, they are doing the concept of half element comparison, right? Any doubt?
Yes. No, sir.
So let's how you write the code. Code is very simple, nothing else. Let us example. First time writing as a for your array data structure. Let's void like boolean, okay, return boolean, data found or not, right? Binary search tree, binary search, okay. and here you are getting any array's value. Okay, and here you return something like a false. So as usual, whenever you are receiving any array, that means it is a sorted array. So you can just create a two variable. One is the left variable, left index. Okay, left index equal to your 0. Let's create your right index. Okay, right index equal to array dot length -1. Correct. And what you are going to do until, let's run here loop, while loop, if left less than equal to right, then what you are going to do, you calculate the mid equal to your left plus right. This is the index, right? Now divide by 2. So you find the mid and check if your here you want to search element as well as right index search element which you want to search. Okay, is the search element equal to a of mid? Is it, if match, if match, then you return true. Okay, correct. If not match, then what you say? You can say if let's s is greater than a of I, then what we need to do? Here concept, if let's this is your array and this is the mid element, and you say ki this is this mid element and s is the greater than, that means your always s available in this direction. So previously your this is the left pointer and this is your right pointer. Now and then you are midding here. In this case, just remove this left to this here, right? This is the left and this is the right. Again, find the mid, right? So what we are going to do, if this s number is greater than the mid number, then your left should be here, mid plus 1. So here is a left equal to mid plus 1. Else what happen? If it is not greater than, that means it's a less than. Less than, that means what happen in the case of less than? Let's, if this is your mid element, this is your left, this is your right. If your search element is the less than here, then you have to search again in this only. So what your R would be, mid minus 1. So here you say our right equal to mid minus 1, and then your logic algorithm complete. If complete loop you just run, okay, and if you find, then return true, else return false. Let's test this. Let's we create one integer array. Let's create some sorted array like 3, 7, 9, 10, 14, 19, 22, 26. Right? So now this is a sorted array, and here you can simply say as out I want to binary search your A element. Let's I want to find the 19. So 90 found or not found. So this what is the error? Oh, I. What is I? I not, this is the mid. Okay. What is the mid you found? It's just compare with the mid, right? And let's run it. So here you say 19 matched. Let's say like what say 20. Okay, 20 false. So this is a very simple algorithms, nothing else. But only precondition, whatever you data structure you pass, that must be sorted. Any doubt, any confusion?
No, sir.
The similarly, you can write the logic for your tree data structure. Here you pass the root node and same logic work for here, right? So any doubt, any confusion, right?
No, sir. So in the binary tree, like here we are always finding if s is equals to mid. So there I think the condition would be is if s is equals to root.
Uh, Anything here you can say whatever the data you're getting. Here your node, whatever the node you're passing. Let's you try to write the same binary search algorithm for tree. First, you have to construct the tree. Here, array by default simplest way you can creating the array, but in the case of your tree, you have to first construct the binary search tree, right? With the precondition, left node always the less than, and right node always the greater than. After you created the binary search data structure, after that you can write the binary search tree. And binary search tree here you pass the root node, and again you checking root node is the less than greater than left right. Accordingly your control is moved to the left direction or right direction. So first you have to write the binary search tree, create the tree, and after that you can apply the search. But the concept is almost the same. This code, this while loop always be, this is the always, this is the always, this is always, this is always. Just only here you are checking the index position. In this case you say node dot value, because they are stored the value at the node level, right? So let's you first try to create the tree and then construct the binary search tree, and after that you can apply the binary search algorithm. What do you think? If you know, I can write the binary tree. What do you think? Are you try?
Yes, sir, we can try.
That's very simple. But first, like you already we have discussed about the how to create a linked list and how one node link to the another node, right? The similar here. You first create a one node object. A node object have a one data part which hold the value. One is the your left part, one is your right part. So you contain the two references of the same node, right? And whenever you go to the left side, you store your left value. Similarly, right side, you store the right value. So let's like here private. So let's you similarly like you static private. You can create like any node, a tree node or simply node, or whatever the node. And here this should be the class, right? Class. And here you can store your whatever the data part. Let's give whatever the value, and this is the your left side, and this is your left. Similarly, your right, right. Now this is your done. Now just create one constructor as well as okay constructor. It will take some value, right, and assign whatever value you have a value, right. Now this is your node part done, and now you can create your tree structure first. Class. Let's write a tree, and here you can just first let's assign your root node, right, and whatever other operation you want to, even you don't need it, just this is sufficient. Now this is your node class and you can construct your binary search tree. So if you how to create, just create a node, your root equal to new node. Just let's initially I got 0.27. Okay, and just after that root dot, then you have to left child, right child. In this way you can construct. Let's in left side I'm going to put value like new node, node like 3. Okay, your left always should be less than root. Okay, and you can construct right like greater than. Let's greater than like 7, greater than like 8. In this way you can create one root node. Root have a one left child and right is a right child. You created one root node here, 7, and 7 have a left child, left pointer have a 3, and right have a 8. Then this we can created this small tree. Similarly, in the this left, let's I want to 1, here I want to 2. So how can you say? Similarly, this is your root left. So I want to say root left dot left equal to, let's key new node, let's 1 should be less than. And similarly, what is the right? Right want to store 2. So in this way, this is your 1, 2. And similarly, here you have a 7, then 3, then 1, 2, similarly 8, 8 here again, just what 9, 10. So similarly, say either this left again, left dot left, 8 should be greater than less than. Here just write like 9. So here say new node like should be 8 less than, and again you say right. So this is the right. So write a 10. So what here you can, here you write the manually code, but this should be need some business logic where you can construct the binary search tree using the algorithm. Okay, so here I'm not writing the code, but just hint. This is the 7 your root node. After that root dot left you have 3. This is the 3, and your right 9. This is the 9, and here you say root dot left dot left is equal to 1. Then here you place it a 1. Root dot left dot right here placing a 2. 2. Similarly, root dot right dot left.
So,
Root dot right
so
dot
2
left
is
here.
greater than 3.
Right. So this is not the binary search, right? So here
Yes,
should
sir.
be like a 2, here should be here 3 somewhere, right? So in this way, the this is there is no logic you have written here key the such follow the criteria. So here should be right, here should be like a something 2, right? And then here should be 3, right? So in this way, you can construct a node. And similarly, instead of manually we are adding element, you can write the some logic to always store value left side, right side. Okay. So let's even uh, ki, now the problem with this data structure, once you create data structure, how you visualize, how you visualize this is the done data, how to print it. How to print the tree element, a root element. In the case of array, you can print it in the for loop 0, 1, 2, 3, 4. Here, how you can print? If you notice this here, so you can visualize your data is created, but how you can read the element. So tree have a, if you notice that this is the root element, and root element have a value 7, and left have a, if you go to left have a value 2, and is again left have a 1, and its right have a 3, right? And similarly, if you again go to the, this is the root. If you go to the right, right have a 9, again left have a 8, again right have a 10. So here in the debug mode, you can find your data store, but really how to print the value, how to read the your tree. So I don't know ki in your syllabus you have a written study or not about how you can read the tree. if any tree, how you traverse the tree. You know anything about how to traversing tree?
No, sir.
Okay. So surely if you need to at least study some theory about the tree. There are multiple algorithms to traverse any tree. First algorithm might be uh, pre-order traversing, then post-order traversing, then in-order traversing, then level-order traversing. Lots of algorithm to read the data from tree. So surely first you have to at least go to the some tree data structure book syllabus, and you know what do mean by the left order tree, right order, yeah, post order traversal, right? Here you can visualize, but how you read the tree, how you traverse the tree. Might be two options here. From here you have two options. You go left or you go right. Agar if you go left again, then here again two options. You can go right or left. So you have to some algorithm which decide in this way you can, in this which way you can traverse your binary tree, right? And once you can created the binary search tree, now in this way you can create a small binary search tree, and similarly we can apply your binary search algorithms. So I think first you go your look your syllabus and figure out first how we can create the binary tree, and then how we can traverse, how we can read the binary tree. And once you are able to read the binary tree, then the next option, how you can create the binary search tree. This while the constructive binary search tree, we apply this condition key always less than left and right value goes. And once you construct the binary search tree, then you can apply the binary search algorithms, right? So just glimpse in this way generally we are constructing your node. And here multiple traversing order like a pre-order, post-order, in-order. So let's simple way. What do you mean by that? This is the left right. Our case like this is the 7, and that is the 2, that is the 9, that is the 1, and that is the 3, and that is the 8, and that is the 10, right? So logically, manually we can create here binary search tree. Why? Because this root left, all left are the less than the root, and all right are the greater than the root, right? Because here you can manually created some condition. So here how you can traverse. So there are let's one traversal known as a pre-order traversal. Okay, pre-order or in order or post order. So this is the some technique ki how we are traversing. Some algorithm you can say. In the case of pre-order, first always you read root element, then left, then right. In the case of post order, you first read left, then right, then root. And in the case of in order, you first read left element, then your root element, then your right element. So this is three strategy where you can read the element. So let us example, we are going to use the this pre-order concept. Means ki first you read the root. The first here you I am reading the root. So I am getting the 7. Then left side. Then you go left. Left have a 2. This is the again root of this subtree. This is the tree. For this tree, this is the root. So again you print the 2. Then again so left. Again left. Here you can some left. Left again this is the root. So you can again print the 1. Then there left, no right. So again, once this subtree left done, then you move the right. After left, you move the right. Then you move the right. Right, you can print here 3. Once this is the right done, again you check. This is the root. Yes, root. Is there any left, right? No left, right. Just done. That means this subtree is done. Your root done, left done, right done. And then this is the seven root. You run done root, you done the complete left, then you move to the right. Right again is subtree. In subtree, you can again root. The first you print this 9, 9. Again left, 8. Then again right, 10. So in this is the way you can print your pre-order traversal. Similarly, post-order traversal. Post-order, first you read left, then right, then root. Similarly, in the in order, first left, then root, then right. So for these all might be you need some pre-understanding, go through, and one by one. First, I think you have to read out the basic, how to create the binary tree, and then how to traverse this binary tree. Next action item, how we can create this construct binary tree. Instead of manually we are ensuring, why not our code? You can just expose some method like add binary tree, yeah, create binary tree. I want to put like 72913, and your system automatically create the binary tree, right? So till now, lots of, because surely you need something pre exercise about the tree data structure to implement binary search tree, right?
Sir, and like the output
Mm.
that is not sorted, so it is always like this 72135. It doesn't matter, like it should be in sorted order.
For question for this algorithm traversing,
Yes, sir.
for traversing there is no any precondition. You can create any kind of binary tree and just read all of it. Let's I want to read in this way, like left root right. So first I want to left, so this is the root, then move to the left. Again this is the root, move to the left. Again to the left, left null, then you print first one. Your left is done, then print right. Left, then root. Root is the 2. Then you can print a 2. After that, you print the right. Right is the again 3. You print the 3. Once this complete left tree done, left, then root, then right. Again left, then 7. Then again right. If you go to the right again you find a tree. The first you're not printing root. First left, then left 8. Then again right, root 9, then 10. So each traversing different order, right? And similarly in the case of post order. So this algorithm simple say कि how you are going to read your element. First you are reading the root, or first you are reading the left, or first you are reading the right. So accordingly different algorithms constructed. So is it so assume कि currently this tree is the binary search tree, and here you can apply binary search algorithm look like the same here. So here whatever written for your, whatever you written for your array, similarly you can write your binary search algorithm for a tree, and here you just pass your node, but your root node. Someone pass the node, root node, and here again similar logic you have type. So but here there is no any kind of length or something. So what you will do, the here concept like in this way, say if your node equal to null, then what you do, else you have to write the code. So instead of I'm just explaining and writing code, just wait, let first you do basic understanding about traversal, right? Is it okay? What do you think?
Yes, sir.
Let's do some homework, and then we have to again discuss. First I think you just prepare some basic tree data structure, put some value and some print the value, and then move to the next how to create a binary search tree, and then how apply the searching algorithm. Right? What do you think?
We will try it, sir, today.
Right? First, you look your table of the content, what your syllabus I mentioned, because the tree is also huge list of topics which we have to cover or study. I don't expect you are going to read, study each and everything. Might be you not need it, right? Right?
Yes, sir.
So let's do first complete the basic things. You know how to create the tree, how to print the tree. Maybe in the pre-order tree, post-order tree, or in-order tree, or level order tree. First know the printing. After that, you next action item would be how we can create the binary search tree. Means that enforce the algorithm like the value should be less than and value should be greater than, right? And once your tree created, and after that you can write again method how I'm going to the searching element. Like here I'm just I don't want to write the code, but let's you should something get the flavor like that. Here like a node, right? Node. Uh, something like a node, and here you say something node. Generally, I'm not want to explain it because key generally in the tree data structure we are using the very recursive call for all the pre-order, post-order, whatever the data you are going to study. Generally, we are going to invoke the recursive function. We are already explaining how the recursive function, how recursive function happen. So in generally tree, whenever you are going to write the create tree, yeah, search tree, yeah, pre-order, post-order, generally we are using the recursive calls to creating a tree, finding tree, or printing tree, or traversing tree. So let's first go your basic things, and then we move again for the tree data structure. Let's look your table of contents, what the things you are going to study, and accordingly your topic wise topics we can cover one by one topics. Right? What do you think?
We will try.
Yes, sir.
Okay. Any other thing you want to discuss?
No, sir.
Okay. So just go about the things what we discuss, and still any doubt discuss questions we can discuss, right?
Yes.
Okay, sir. Yes, sir.
So can we close the call? What do you think?